Now remember, my hint to you is always find, if you're ever doing double angles, to find our cosine 2 alpha first. But look what they gave me. They already gave me cosine 2 alpha. So don't go ahead and find sine 2 alpha. That's not going to help you at all. That's just going to be a waste of a whole bunch of space and time. As soon as we have cosine 2 alpha, which we have, we are going to jump right into our double angles. Okay, so we look at our double angle formulas, and you can either get, or half angles actually, we're going to use our half angle. So we can either get, we're just going to do the cosine. So we're going to say, let's just write down our half angle thing first. So that equals the square root of 1 plus cosine of x all over 2. But what I'm going to do is I'm going to plug that 2 alpha in for this x, which means I'm going to plug it in for that x. And the good thing is I know what cosine 2 alpha actually equals. That's our whole goal. So when I put all this stuff in, I'm going to have cosine of 2 alpha. That's not an alpha, that's an alpha. Divided by 2. Well, that will cancel out, and I'll just have cosine alpha. And it's all over 1 plus cosine of 2 alpha. All over 2. But our whole goal was that I could put everything in there and have cosine alpha by itself. I have cosine alpha by itself. So we have cosine alpha. And not only do I have cosine alpha, I have all numbers on the other side, because we are going to, I'm going to jump right into it. I'm going to say 1 is 5 over 5 plus my 3 over 5 over 2. So I just go ahead and I do that in my head so I can have stuff written down. I don't make stupid mistakes. And then I have 5 over 5, and then I just have to add 3 to that. So that's going to be 8 over 5 equals square root of 8 over 5 over 2. You can either do this in your head or go ahead and write it out. I'm going to put a little note saying I'm kind of doing this in my head, where I do the 8 over 5. I multiply by that reciprocal on the bottom, so that's 1 over 2. Well, the 2 and the 8 really cancel each other out, and I'm left with 4 on top and a 1 down here. So that's 4 over 5 times 1. So our cosine of alpha is going to equal square root of 4 over 5, which is just going to be 2 over the square root of 5. Did we get that? Did we make mistakes? Does at least what I'm doing make sense? Especially if you weren't here for most of that. Brian, does that make sense, what I kind of did? No. No?
I admire your honesty.
Yeah, I admire your honesty. No.
The slightest.
Okay. Did you do the homework at all?
I tried. It didn't make sense.
Okay. Do you have the double angle sheets at all?
Yeah, I printed all that stuff.
Okay. And you watched the videos on it?
Yeah.
Because the whole thing about this is just plugging in for x. Alright, is plugging in 2 alpha for that x. So you have to have your double angle sheets, otherwise it's not going to make sense. Otherwise you got to come see me about that, because this is like the cornerstone of that whole section, that you can do this. Alright, so we have 2 over square root of 5. How do I know if it's positive or negative? Yeah. It's in quadrant 1. Well, to be fair, I really only know that 2 alpha is in quadrant 1, right? How do I find what quadrant alpha is in? Yeah. You just cut it. Yeah. We divide everything by 2. So that'll be 0 degrees is less than 2 is less than 45 degrees. And if... What happened? Oh. I see it. I see it now. That should be just alpha. Alright, so that's in the first quadrant. But realistically, I just need to know the starting point. The ending point has to be the barrier of the next quadrant, because we had that problem in the homework where it actually went past it. It was like 0 to 3 pi. Or it wasn't 0 to 3 pi. I think it was, pi to 3 pi, which meant it was over here and went all the way around kind of thing. That doesn't make sense. Know your starting point, and you're just going to stop. It just gets stopped at that quadrant. You can't go to more than 1. So this one starts at 0, so it's automatically going to be in quadrant 1 as it is. So this is going to be alpha is in quadrant 1 as well. So since it's in quadrant 1, everything's positive. We are good with cosine alpha equals that guy. As soon as we get cosine alpha or sine alpha, if you find that first, everything goes back to what we did a month ago, where we say, well, I know that sine squared alpha plus cosine squared alpha equals 1. We're just going to plug in that 2 over square root of 5 in for our cosine. So we'll have sine squared alpha plus 2 over square root of 5 squared equals 1. We're going to have sine squared alpha equals, I'm going to shortcut this, so I'm going to square it and I'm going to subtract it from the other side. So we're really going to have 5 over 5 minus 4 over 5. So I squared this, which became 4 over 5, and I subtracted it from both sides, so it's going to look like that. Oh, I don't need that square then, because I took... Oh, I do need a square, never mind. Alright, so that's going to equal 1 over 5. So sine squared alpha equals 1 over 5. Take the square root of both sides, and you're going to see that sine alpha equals... Now, a whole bunch of people did this on the test. They left... They did... this isn't correct. Well, it's not necessarily incorrect, but they leave it as that. A lot of people left square root of 1 as just square root of 1, and they just hung on to it throughout the entire thing until they got to the answer. What's the square root of 1? 1. So don't have square root of 1s floating around. It's just room for you to make silly mistakes. All right, having a square root just hanging around, and then you have like square root of 1 times some number, and you're just like, I'm not sure how to simplify it. Square root of 1 is just 1. All right, if you know the square root of something, just take the square root of it. If you know the square root of 4, it's 2. Square root of 9 is 3. I don't want to continue on, but just take the square root of it to simplify it. The easier it's written, the less chance you have to make mistakes. Okay, any specific questions? I know, Brian, you weren't here for this, but do you have any specific questions? No? Oh, okay. All right. Yes?
For the first part, when you did cosine and then you did like the half angle identity, you also use the double?
You can use a double angle, and if you look at the double angle, it's going to turn pretty much into this exact same thing. It's just, so what Alina's saying is, instead of using our half angle, we just go ahead and say cosine of 2 alpha equals whatever double angle you want to solve for, either sine or cosine. It'll all work out the same. It's just this is a little bit of a shortcut because you can just plug stuff in and you don't have to take square roots of both sides, move stuff over. Everything's already moved over for us. That's the only advantage of this. But if you want to just plug that into the double angle, come up with the exact same answer, same stuff. Good. You came up with the same answer though, right? Yep. Okay, other questions? Yeah.
I guess like partially more like a homework question.
Okay, should I go to the homework?
I mean, sure.
Okay.
It was, question 49.
Okay, no, let's take a question.
Like, how do you know when to like set it equal to the value you're given versus plug the value in?
I'll have to look at what you mean. Just a second. So number 49 specifically.
Yeah.
So how do you know if you're plugging it in or setting it equal? Are you talking about like the very first step?
Yeah.
So the very first step I would do is I'm going to use the half angle identity, right? So I'm going to use the cosine of, let's just keep it with alpha over 2 is going to equal the square root of 1 plus cosine alpha over 2, right? Is that what you're talking about?
Yeah.
So because these two things are actually equal, it tells me I can either use this or I can use this. So I'm going to replace all of this for this entire thing. I think that's what you're asking, right?
Yeah, so it's basically just as long as you're not given, like, when can't you do that then? Because I mean...
You could technically always do that.
Yeah.
So,
is it just like easier sometimes to keep it in the equation rather than set it equal to? Like, is that the only reason you wouldn't do it?
are you talking about like when we have cosine 2 alpha over 2?
Yeah.
So we have. Did I do something wrong? Oh, okay. Yeah, if we want to see how I'd finish this one, I would just have 1 plus
Yeah,
cosine alpha. I would square both sides. I would multiply by 2.
Yeah.
I would subtract 1.
I get how to do it like afterwards. I just don't know when to just like.
When to actually replace it.
Yeah.
So you need to replace it if it actually is. Let's look at the bell work really quick, because this is a really good question.
Yeah, like I did.
When do I replace?
Because can't you do it like pretty much any time as long as like it's a double or a half? Like can't you always do it then?
As long as, so see how I have cosine 2 alpha?
Yeah.
As long as I have cosine 2 alpha, I can replace it.
But okay, like for the bell work, I mean,
Mhm.
can't you like just set it equal to, I guess, if you really wanted to, like equals, like that. This is what I thought Lena was talking about. Like
Yeah.
equals 2 cosine squared.
So it depends on which one she's doing. So she probably took out her double. So yeah, that's definitely a possibility to solve. I just don't want to do 2 ways.
Okay.
But I can definitely show you how to set that up. So what Lena did is she noticed that, so she went ahead and looked at her identity sheet for this one.
Yeah, I mean, like, is there a way to tell like which is easier? Like,
There is no technically easier way. But let's just look at, let's make sure we're paying attention. Oh, did we? On which one?
On what she asked, I don't know.
I'll talk about what she asked.
Okay.
So what she asked is it okay to look at your double angle identities? So say you can look at yours and it says cosine of 2x equals, what one should I pick? Let's just do the 2 cosine. 2 cosine squared minus 1. So I think that's what, Lena, you're talking about, right? So she recognized, hey, if I just replace this x with alpha, and I replace this x with alpha, well, hey, I already know what cosine 2 alpha equals. All right, cosine 2 alpha equals 3 over 5. So she could plug in 3 over 5 equals 2 times cosine squared alpha minus 1. So then in solving this, I would add 1 to both sides. So I'd add 1 to both sides. So we have 3 over 5 plus 1 equals 2 times cosine squared alpha. I would divide by 2, and then I would take the square root. But what is the half angle? Our half angle already has that set up for you. So remember this. Remember this. I have 1 plus 3 over 5 divided by 2, and I just worked my way to it, starting off here. Okay? Does that make sense? Well, I can start here and end here, but just remember I have 1 plus 3 over 5 divided by 2. Now let's look what we had before when I used the half angle identity. Possibly. I had 1 plus 3 over 5 divided by 2 square root. But this method allows you just to plug it in. The way Lena did it, you actually had to solve your way through it. Okay? Does that make sense? Why I choose to do this? Because if we do it, I'm going to call it Lena's method from now on. But if we use her method, she actually has to solve to get to here. Where the half angle, because I already know what I'm going to replace in my head, I can just plug numbers in. Because I already know I'm going to have cosine 2 alpha here. I'm going to plug in the 3 over 5. So maybe in my first step, I already have that done. Where Lena has the, cosine of 2 alpha equals 2 times cosine squared of x minus 1. She has to move stuff. But either way works. Either way gets the same answer. Okay. Does that kind of...
Yeah.
Peyton, does that make sense of what she was asking then?
Yeah.
Okay. So you can always use double angles. So if you're really confused about using the half angle, go ahead and use the double angle, right? Say cosine of 2 alpha equals 2 times cosine squared alpha minus 1. We know cosine 2 alpha, and then just solve for it. It was just, this was kind of a shortcut, but if you don't like it, take the long road. It's just as good. Okay? All right, other questions on the homework? We don't have an absorbent amount of time, but we can do a couple of them. You can ask a question. It's fine.
No, not right now.
Not right now. Questions on the homework? For realsies? We spent almost half the other class doing it. Okay. Okay. I mean, like I said, you always have the answer guide. And if that doesn't make sense, that's when you ask a question, right? So if you guys got it by looking at the answer guide, then good on you. Okay, then let's just do today's lesson. I like today's lesson. It takes kind of a step back. It's basically, can you use the unit circle and can you add? Can we at least add? I'm going to give you the unit circle on the test. Okay? I'll give you the unit circle on the test. So what I'm asking, in the very first question it says, name 3 angles that satisfy the following. That cosine x equals 1. In other words, I'm looking for when is that x value equal, right? We have the x, y values on each of these points. When is my x value 1? In other words, I'm saying, what is the inverse, or what angle? So I'm looking for an angle, 3 angles actually, that have 1 as the x value. So let's go ahead and look at our unit circle, or you can just think in your head, where is x equal to 1 on our unit circle, or when is cosine equal to 1?
0 degrees.
At 0 degrees, so right here. Right there. So I'm going to mark that on there. So at 0 degrees, so we know for a fact one of our degrees is 0 degrees. Does it ever show up again on the unit circle? No, because we just have -1. We have -1, we got 1, we got 0, we got 0. Okay, so we have 0 degrees. But what we can do is we can say, well, it's at 0 degrees and it's also at, what degree would that be? That's where the adding comes in, guys. So that's 2 angles. Let's get our third angle. 70, yeah, oof. Adding's on point today. So 720 degrees. So that's 3 possible angles. However, I'm never going to ask you to show 3. I'm either going to ask you what is it on the unit circle, or I'm going to say what is every possible answer. All right? So that's what we're going to be working on here. Find all the real numbers that satisfy cosine x equals 1. Well, we started off. We said the very first positive one, well, not positive, but not negative, is 0 degrees. And then we have 360. And then we have 720. Well, to go on forever, I'm just going to keep going around that circle and stopping every 360 degrees. So this is going to go on and on and on. Yes?
Would it be plus or minus x plus 360?
Kind of. Not plus or minus. We'll get there. Yeah, but you're on the right track. You're absolutely on the right track. Because we are adding 360 each time, right? That's what you saw. You saw that we are adding 360. I'm adding 360. I'm adding 360. And we would just keep going on and on and on. And rather than writing out all of them, just like John was trying to do, he's trying to come up with a formula where I can just write one thing that stands for everything here. I just want to make sure I'm doing this the exact same way. So what I said was my very first angle that's not negative. We all start with the first angle that's not negative. I say not negative because 0 is okay to start with. So I'm going to pick my lowest angle, so that's 0 degrees. And we are going to add 360. We're just going to add 360. We're not going to subtract. It's not going to be plus or minus. We're just going to add 360 degrees. And however many times I add it tells me what angle I'm at. All right, if I add 360 twice, I'm going to get to 720. If I add it 3 times, I'm going to get to 1080, so on and so forth. So right here is every possible angle where cosine x equals 1. Because this is just starting at 0 and then spinning around 360 however many times is related to k. Another way we could rewrite this is we could rewrite this as 2, I think I usually put the k in between. I didn't there, but usually you put the k in between. You say 2k pi. I don't care where you put the k. If you'd write the k, 2 pi k. I'm not going to take any points off. It's just traditionally, I think we usually put it right between there. And in fact, just for the lesson, I'm going to say it's 2 pi times k. It makes more sense that way when you're first learning it, because it's a full revolution, that's 2 pi and k number of times. So I don't think that's the hard part about this lesson. The harder part is our set builder notation that we have to use to write this, because 360 times k or 2 pi k doesn't mean much. All right, it's not an actual setup thing. So what we're going to use is something called set builder notation. And what we're going to do with set builder notation is we're going to say, well, x, so that x right there, x exists, and then we'll put a line. That line right there means such that. So x can be anything such that x equals 360 degrees times k, because that 0 is going to cancel out. I'm not going to put 0 plus something. Now we have to put a little something extra in there. Right below it or off to the side, doesn't really matter. You have to put, we have to put where k is an integer. Now I had to look at my notes because I never write it that way. In math, you almost never write out like a full sentence like this because we always try to shorten things. So I don't think the book uses a notation, but this will save you a lot of time. Is you're just going to write k is an element of the integers. All that's saying is that k is an integer. All right, this is our symbol for integers. This is a symbol that basically says it's in that group. It's an element of. I'm part of that. So k is part of the integers, which says k has to be an integer. I think this is way easier to write than this over and over and over, and you will have to write them a bunch of times, so why not just write that? Yeah?
Because it's just plus, don't we have to have, like absolute value somewhere?
Nope. We're only worried about the positive. Well, we don't need plus or minuses.
No, but like, isn't that why you need the absolute value? Because it's just plus?
Well, no, that's why we don't need plus or minus, because this could be a negative one. So we could have negative 360 degrees. We could have negative 720 degrees. So that's why we don't need to write, because John had plus or minus 360 degrees. We don't need that because k can already take that place. K can already take that place of negative. K can be -1, which gives me that negative. So I can go backwards on the unit circle, right? So that's why we don't need absolute value signs. We don't need pluses or minuses. K take care of all of that for me by saying that k is an integer. K can be negative. Does that make sense, though? So k can be negative. All right, so two things. We already did identities. Identities are true for every single value. Conditional equations are quick... or identities or equations, conditional equations, have at least one solution. Doesn't mean they work for all of them, but they have at least one solution. That's the only difference between the two. Identity, all, conditional, at least one. Okay, we're supposed to find all the real numbers that satisfy the equation cosine x equals 0. So where on the unit circle does cosine equal 0? And if you need to, you can take out your unit circles. Yes, sir.
90 and 270 degrees.
90 and 270 degrees. I'm going to use pi for this one, because we do have to know both ways, just in case on the test I say you have to use radians or you have to use degrees. So let's go ahead and say this is pi over 2. But it also occurs down here. It also occurs down here, which is 3 pi over 2. Well, this changes the game a little bit. Over here, I had to go 360 degrees before I can get back to that dot, right? I had to go 360 degrees before I could get back to that dot. This time, if I just go pi units, or 180 degrees, I already get to my next dot. And then I add pi units, I get back to this dot. I add pi units, I get to this dot. So every pi I go, if I start here, every pi I add is going to get me to a dot that exists. So we're going to look at the fact that, hey, from here to here is just plus pi. From here to here is just plus pi. And we just keep going around in the circle, adding pi, adding pi, adding pi. So that tells me, as long as I tell someone where I start from, I just need to keep adding pi, and it's going to be one of my solutions. So since it repeats every pi, we're just going to say x is going to equal my first positive angle. So first, I'll put non-negative. First non-negative angle. And it's important I list that because we're going to have negative ones in a second. We have to find that first positive one to actually list it. So I find my first positive or non-negative angle, and then for this one I just add pi to it. I add pi, but I don't know how many pi's I'm going to add, so we're going to say pi times k. Because if I start here and I add 2 pi, I get to one of these circles, right? If I added 3 pi, I'd get here. No matter how many pi's I add, that's why I write it. Now all I have to do is put it in set builder notation. And that is, x can be anything such that x equals pi over 2 plus pi k, or k pi. I'm not really too concerned with how you write that. Such that k is an element of the integers. And when you actually work with set builder notation, we're not actually working with it. We're just using it to give answers. A lot of times you'll actually put this inside your set builder notation. Okay, so just up till now, if it appears once and I have to go around 360, we're adding 360 or 2 pi. If we have 2 dots and they're separated by pi, we're just going to add pi and a certain number of k's to that. All right, let's say that cosine x equals -1. So cosine x is going to equal a -1. Well, I'm just going to run through this one really quick, because that's going to be at pi. And this is almost exactly the same, where x is going to equal pi plus, well, it only occurs once on my circle, so I need to add 360 to it to get back to it. Well, let's not use 360 pi, let's use 2. Let's keep it in radians. We're going to say, instead of 360, we're going to do 2 pi. 2 pi k, which means I can already set up my set builder, which is x can be anything such that x equals pi plus 2 pi k, where k is an element of the integers. All right, everyone look at your unit circle. Find where cosine x equals 2. Sri's shaking her head. It doesn't exist. That is not on our unit circle. All right, so that isn't on our unit. It's actually way out here. So we're going to put no solutions. And this works for sine and cosine. So say we have, let's just say cosine of x equals s, or sine x equals s. If the absolute value of s is bigger than 1, then you're going to have no solutions. So in cosine and sine, did I say anything about tangent? This isn't true for tangent, because think about tangent. Tangent sine over cosine, right? So sine could be super small, it could be like 0.1, and cosine could be 1, and it'll be like 100. All right, so tangent can be as big as it wants, but cosine and sine need to be less than 1 when you take the absolute value for us to be able to do it. Otherwise, there's no solutions. All right, that's a big one because I like to trick you on tests where I put that on there and then you wait, you spend like an hour trying to solve it and it's like, oh, there's no solutions, you're a jerk. Now you know there's no solutions to those. All right, now we're going to look at sine x equals negative 1/2. Okay, where does sine equal negative 1/2? How much time do we have actually? Maybe I'll do less questions and more just telling. All right, so sine of negative 1/2 is here. And it's also here. And that occurs because our sine is negative in the third and fourth quadrant. So whenever I have a sine that isn't 1 or 0, it's going to be in alternate quadrants. If it was 1/2, it would be here and here. Well, that leads us to a small problem. Ooh, I should probably label it, huh? 7 pi over 6. And then 11 pi over 6, right? Yeah, 11 pi over 6. If I have 7 pi over 6 and I add 180 or pi to it, do I end at the other circle? If I add pi to this, is this one of my answers? No, it's not. I would need to add some weird fraction, and we're not going to do that. We're going to say, well, I can't add just pi to it, so for this one, I'm just going to say I'm going to keep adding. I'm just going to keep adding 2 pi to it. So one of our possibilities, because I can't just add pi to it, is x equals 7 pi over 6 plus 2 pi k. Because I can't add pi to it, I'm just going to revert to, I'm just going to keep going around and catching it every single time I go around. Likewise, x could also be 11 pi over 6 plus 2 pi k. Because I'm going to start here and I'm just going to keep going around and say I'm going to use those. I can't use that half angle thing kind of is a trick. I add pi. It doesn't work here, so we have to keep adding 2 pi. All right, that changes our set builder notation just a little bit. Because now we're going to have two possibilities, and how we're going to write it is x such that x equals 7 pi over 6 plus 2 pi k, or x is allowed to equal 11 pi over 6 plus 2 pi k. Such that k is an element of the integers. Okay, so if our points, if I just have one point, we add 2 pi. We add 2 pi. If I have 2 points and they're 180 degrees away, we just take that first point that's positive, add pi, add pi, add pi, we're good. If I have 2 points that aren't pi away, we do 1 for 1, and we do another one for another one, where we add 2 pi. Okay, those are basically our only options. Okay, I'm going to skip to tan x of negative 1.34. Primarily because this one doesn't follow that sine and cosine rule like I said. If it's greater than 1, it's okay. What we need to do is it's not on a unit circle, so you'd need to take out your calculator for this one, and you'd have to actually find the tangent inverse of negative 1.34. And I'm going to do it in degrees. So I don't know what mode your calculator's in, but I'm going to do it in degrees. So our x is going to actually equal that. So just check to make sure you can put yours in degree mode, because you will have to use it. And make sure you can get out 53.3 degrees. Here's where we have to be smarter than our calculator, though. So negative 53.3 degrees is a little past here. That's our negative 53. And it's good there because what's our tangent in the fourth quadrant? Well, that's negative. Our tangent is negative. Is tangent negative anywhere else on the unit circle? you have a question, Sri?
Okay, how'd you know like where to put the dot?
Each one of these is 45 degrees.
Yeah.
So I just said, well, if that's negative 45 degrees, negative 50 is, it's not accurate. It's not accurate at all. All I want to do is I want to place it accurate enough that I know what quadrant it's in. Okay, and it's more for this drawing's sake than anything else. Is because in quadrant 4, tangent is negative. But tangent is also negative in our second quadrant. Tangent's also negative in our second quadrant. And why that's important is because that point is going to exist up here as well. If we have a negative 53.3 here, we're going to have something here as well, because our values always repeat. Remember, unit circle, it always repeats itself over and over and over. So you just have to recognize if it's negative, I'm going to go back up here. So that means all we need to do to get that degree is we just have to do x. Our other x is going to equal negative 53.3 degrees. And what am I going to do to get to that other point, do you think, if it's straight across? What am I going to add to it? Yeah.
180.
I'm going to add 180 to it. So plus 180 degrees, make sure I got that right, is going to equal 126.7 degrees. So this is actually 126.7 degrees. Now, like I said, in set builder notation, I want to have my first positive. I'm going to use my first positive angle. Bless you. And so we're going to say x such that x equals that 126.7. Would it be okay if I used a negative? Possibly, because we're just adding and subtracting, but the tradition is that we use the first positive one. And we're going to add 2 pi or pi to it. Pi, yep. So we'll add pi k to it, such that k is an element of z old integers. Yeah?
I have a question like on an earlier problem. The sine x equals negative 1/2.
Oh, I can't go back. Oh, which one? The
The sine x equals negative 1/2.
oh, yeah, yeah.
And we said that we had to add 360 so we could keep coming back, but why wouldn't we just add 120? Because we could just go to
So you want to jump right to this point?
yeah.
Well, then how do we jump back to this point?
Oh, okay. Never mind.
And how are we sure? And if I go the opposite direction, then I'd subtract 120, I'd end up here.
Yeah.
You just run into a whole bunch of problems that just can't sort themselves out. That's why we say, okay, no shortcut. I'm just going to list all these answers, and then I'm going to list all these answers. I'm just going to put an or between it, because there's no real shortcut your shortcut would actually be longer, because it'd be add 120 unless you're subtracting it, in which case you would actually subtract, you'd be you'd have to explain it. Does that make sense why we wouldn't want to do that? The only time we want pi is because it just repeats itself. This, 2 different numbers, because I have to get back here. That's a good question. I would have that question. Other questions?